I'd like to thank the organizers for giving me the opportunity to give a talk, and thank you all very much for coming to my talk. Okay, so today I'm going to be talking about large monochromatic tight cycles in two-edge colored complete four uniform hypergraphs. And this is all joint work with my supervisor, Alan Lowe. Okay, so in this talk, we will consider edge colorings of the complete graph, or later complete K-uniform hypergraphs. And here by an edge coloring, we just mean the assignment of colors to the edges in any way. So not like a proper coloring, as you might find in other parts of the literature. So here you have an example of a red-blue edge coloring of the complete graph on 5 vertices. And then by a monochromatic subgraph, we mean a subgraph where all the edges have the same color. So for example, here's a monochromatic cycle in this red-blue edge coloring of K5. Okay, so we're interested in questions about what sort of structures we can guarantee in every red-blue edge coloring, or maybe also with more than just 2 colors of the complete graph. Okay, so just as a warm-up, we'll consider this question, namely, does every 2-edge colored Kn contain a monochromatic spanning tree? Okay, so this is often given as an exercise in a graph theory course in the form of, is it true that either graph or its complement is always connected? Okay, and so the answer turns out to be yes, this is true. And so to prove this, we'll assume that there is no blue spanning tree. So in particular, there must be 2 vertices, u and v, such that there's no blue path from u to v. Okay, so 2 vertices here, u and v, such that there's no blue path from u to v. Okay, so in particular, the edge from u to v has to be red. And now if we consider any other vertex, call it w, then if both the edges uw and vw were to be blue, then we would have a blue path from u to v. So at least one of these edges has to be red. And then we see that w is also connected in this red component to u and v. So, and since w is an arbitrary vertex, yeah, the graph induced by the red edges is connected, so there's a red spanning tree. Okay, so what other sort of problems could we consider? So there's a conjecture by Lehel, which states that every red-blue edge-colored Kn can be partitioned into a red and a blue cycle. And here, to avoid some trivial counterexamples, we consider the empty set, a single vertex, and a single edge to be cycles. So then here we have, again, a coloring of K5, red-blue edge coloring. And here we have a partitioning into a red cycle and a blue edge, which we consider to be a cycle here. Okay. And so this is proved for large N by Woodruck, Rödel, and Semeretti using Semeretti's regularity lemma. And then later, Allen improved on the bound on this N0 by avoiding the regularity lemma. But then actually this was later proved for all N by Bessie and Thomasé, who gave an elementary proof which only uses, which is only like 7 pages long. Okay, so from now on, just so I don't have to repeat myself all the time, we will assume that N, the number of vertices, is large enough and that all cycles are vertex disjoint and monochromatic. Okay, so what could we consider next? We could also ask for, what about if we have more than just 2 colors? Okay, and then there was a conjecture by Erdős, Javas, and Piper from 1991, which states that every RH-colored Kn can be partitioned into R monochromatic cycles. So for R equals 2, this is true by the proof of Lyell's conjecture. And they gave first result towards this, namely showing that you can do it with a constant R squared log R cycles. And then this was later improved by Javas, Rushinsko, Sarkozy, and Semeredi to 100 R log R cycles. But then actually turned out that this conjecture is false. Namely, Pokrovsky showed that there are counterexamples for all R at least 3, where there's at least one vertex that you cannot cover with R monochromatic cycles. Okay, so he made a new conjecture saying that every RH-colored Kn contains R monochromatic cycles that cover all but a constant number of the vertices. And he has since proved this for R equals 3, but is still open for larger R. Okay, so then we could also consider similar problems for hypergraphs. So what is a hypergraph? And we also have to say what a cycle is in a hypergraph, because there are different notions of cycles in hypergraphs. So a k-graph H, or a k-uniform hypergraph H, is a pair of sets V of H, E of H, so a set of vertices and a set of edges, where each edge is a k set of vertices. And a tight cycle is a k-graph with a cyclic ordering of its vertices, such that its edges consist of k consecutive vertices. So for example, if you want to draw a free uniform tight cycle here, then the first 3 vertices in the cyclic ordering form an edge, and then the next 3 vertices form an edge, and the next 3, and so on all the way around. Okay, so that's a tight cycle. Okay, so, and then for these sort of problems in k-graph, we again we consider any set of size at most k to be a degenerate cycle, again to avoid some trivial counterexamples to these sort of results, just as we did for Lyell's conjecture. Okay, so what sort of results are known for hypergraphs? So there's a result for R colors, namely a theorem by Bustamante, Korsten, Frankel, Pokrovsky, and Skokan from 2020, where they showed that every RH-colored K and K, so here we mean the complete K-uniform hypergraph on n vertices, can be partitioned into at most a constant number of monochromatic tight cycles, where the constant depends on R and K, but this constant is quite large. Okay, so we could also ask, can we do with a lot fewer cycles if we restrict ourselves just to 2 colors? And then this was studied in the free uniform case, first by Bustamante, Hahn, and Stein, who showed that every red, blue, edge-colored complete free uniform hypergraph contains a red and a blue tight cycle that together cover almost all of the vertices. Okay, and then we also have an exact result in the free uniform case, namely this theorem by Garvin, Mycroft, Lang, Low, and Sanwasa Matamala, who showed that every red, blue, edge-colored complete free uniform hypergraph n vertices can be partitioned into 2 monochromatic tight cycles. Okay, and note that here it doesn't say a red tight cycle and a blue tight cycles, it says 2 monochromatic tight cycles, and that's actually because it's not true, the statement is not true if you were to insist on 1 red and 1 blue one, because there's a counterexample showing that if you insist on 1 red and 1 blue one, there's at least one vertex which where there's at least one vertex which you cannot cover. Okay, and so we proved an analogous result as the Bustamante, Hahn, and Stein result here for the 4 uniform case. Namely, we showed that every red, blue, edge-colored KN4 contains a red and a blue tight cycle that together cover almost all of the vertices. Okay, and we also showed a result for the 5 uniform case. Here we only were able to prove that you can do it with 4 monochromatic tight cycles, but we really believe that 2 should be enough to cover almost everything. Okay, so if you have any questions about these results, then I would be happy to answer them now. So then we also considered problems in a related area, namely in the Ramsey theory for hypergraphs. This turns out to be quite related in the approach that we take. So what is the Ramsey number for hypergraphs there? Given a uniformity k at least 2 and a k graph h, the Ramsey number R of h is the smallest integer n, such that every 2 edge-colored complete k-uniform hypergraph on n vertices contains a monochromatic copy of h. So what sort of results do we know for cycles? So just in graphs, in normal graphs, the Ramsey number has been known since the 70s. So if we have an even cycle, then the Ramsey number of the cycle is about 3/2 times the length of the cycle. And if the cycle is odd, then the Ramsey number is about twice the length of the cycle. And here you have the precise result for that. Okay, and so what about hypergraphs? So there's a result by Haxel, Wujak, Peng, Rödl, Rusinski, and Skokan from 2009, who asymptotically determined the Ramsey number for 3 uniform tight cycles. And again, it depends very much on the parity of the length of the cycle. So if the length of the cycle is divisible by 3, then the Ramsey number is about 4/1 times the length of the cycle. And if the Ramsey number is not divisible by 3, then, sorry, if the length of the cycle is not divisible by 3, then the Ramsey number is about twice the number of vertices in the cycle. Okay, and we showed first result for 4 uniform graphs in this area. Namely, we showed that the pattern continues, that if the length of the 4 uniform tight cycle is divisible by 4, then the Ramsey number is about 5/4 times the length of the cycle. Okay, and so and I'll explain quickly here why this is. The upper bound here is tight, so why do we have this lower bound of 5n minus 1? So the construction goes as follows. You take 2 sets of vertices, one set x of n minus 1 vertices, and a set y of 4n minus 1 vertices. And so now how do we color the edges? We color all the edges that are entirely inside y, we color blue, and every other edge we color red. So all the edges that are entirely in x, and all the edges that have some vertices in both are colored red. Okay, and I've shown all types of edges here. Okay, and so actually this does not even contain a monochromatic matching of size n. Okay, and of course that also shows that it doesn't contain a 4 uniform tight cycle on 4n vertices, because you could just take every 4th edge in the tight cycle and that would give you a matching of size n. Okay, so why does it not contain a monochromatic matching of size n? So you definitely can't have a blue matching of size n, because then it would have to be entirely inside y, but you only have 4n minus 1 vertices in y, but you would need 4n if you would have a matching of size n, because each edge has 4 vertices. And then you also can't have a red matching of size n, because every red edge contains at least 1 vertex of x, and there are only n minus 1 vertices in x. Okay, so now I will talk a bit about the proof, how we prove these sort of results. So a common approach to our results. So both our results are about finding large monochromatic tide cycles in red, blue, edge-colored complete 4 uniform hypergraphs. So what we use is a hypergraph version of what is called Bouchard's connected matching method. So this is a method that reduces finding monochromatic cycles to finding what are called connected monochromatic matchings. Okay, and I will now explain how this works. And just for some simplicity, I will stick to the graph version and not talk about hypergraphs in this part. Okay, so you have a red, blue, edge-colored KN. So what is the first step in the method? The first step is to apply the regularity lemma. Okay, and what do we apply it to? We actually apply it to the graph induced just by the red edges, and then we get a regular partition. But this regular partition is actually also a regular partition for the graph induced by the blue edges, because these graphs are complements of each other. Okay, so we get so a partition of the vertices into clusters V1, V2, V3, and so on. Okay, and so if you don't know what the regularity lemma does, it basically means that you partition the vertices into clusters, and then most of the pairs of clusters will be what is called regular, meaning that the edges going between these clusters behave in a random-like way. So if you take some, so if V1 and V4 is a regular pair, then if you take some subset in V1 and some subset in V4, then the number of edges going across the subset will be about what you would expect given the density between the whole clusters. Okay, so and then along with this partition also goes what is called the reduced graph. In the reduced graph, you have one vertex for each cluster in the partition. And then if a pair of clusters is regular, then you have an edge in the reduced graph. So if V1, V4 is regular, then you would have an edge here. So 1, 2, 3. Okay, but now we also have a coloring. So we also want to color the edges in the reduced graph. So we color the edge 1, 2, 4 red if most of the if more edges between V1 and V4 are red than blue, and otherwise we color it blue. Okay, so let's say, for example, 1, 4 is red, 1, 2 is red, 4, 5 is red, 3, 5 is red, 3, 6 is red, and then we also have some blue edges, and then maybe also some irregular pairs. Okay, so now what is the second step? The second step is to find a monochromatic component in the reduced graph. And by that, I just mean a connected component in the graph only induced by one of the colors. Okay, and we want to find such one which contains a large matching. Okay, so for example, we could take here the edge 1, 2, the edge 4, 5, and the edge 3, 6, and noting that all of the red edges actually form a component. Okay, so this is also called a connected matching because it's a matching, but you also have these edges connecting it. Okay, so once you have that, then we use this matching to construct the cycle in the original graph. Okay, so how do we do this? First, we look at each edge that we have in our matching. So say the edge 1, 2, and then given our regularity properties, this means that we can find a long red path covering almost all of the vertices in these two clusters like this. And then we similarly do this for all the other edges in our matching. Okay. And now crucially, because we chose our matching inside a connected monochromatic component, we have these edges 1, 4, and 3, 5, which actually allows us then to connect some of these paths together, like so, and actually allows us even to go then from here all the way around and connect to this end of the path, and then we have connected everything up into a cycle. Okay, so that's Butchak's connected matching method, which turns the problem of finding cycles into a problem of finding matching inside connected components. So now what does this actually mean for our results? So this reduces to our results to finding matchings in monochromatic tight components, and I'll explain what that is in a second, in an almost complete foregraph. So now here we're, of course, applying a hypergraph version of the regularity lemma, and then the reduced graph will be an almost complete foregraph if we are starting off with a foregraph. Okay, and we have tight components here because we want to end up with tight cycles, and that's the notion of component you need to use to be able to end up with tight cycles. So what is a tight component? So a set of edges F in a foregraph, H is called tightly connected if for every pair F, F prime, and F there exists a sequence of edges, such as the first one is F, the last one is F prime, and consecutive ones share 3 vertices. Okay, and here is a sort of a picture of a tight path, and sorry, not a tight walk from F to F prime. Okay, and then a tight component is just a maximal tightly connected set of edges. And then a red tight component is a tight component in the foregraph induced only by the red edges. Okay, so what does this mean for our results? So if H is a red-blue edge-colored almost complete foregraph, so the reduced graph in our setting, then our first result, which I have, which is shown again here, and says that every red-blue edge-colored KN4 contains a red and a blue tight cycle that together cover almost all of the vertices. This is reduced to finding a red tight component R and a blue tight component B in H, in this almost complete red-blue edge-colored foregraph, such that their union contains a matching covering almost all vertices. And similarly, the second result for about the Ramsey number of the Fourier uniform tight cycle is reduced to finding a monochromatic tight component in H that contains a matching covering a 4/5 fraction of the vertices. And the 4/5 here because we want to find a tight cycle of length 4n in a graph which has about 5n vertices. Okay, so I will now, so basically the the first step in the proof is finding good components that contain these matchings. So we're looking for good red and blue type components. Okay, so I'll now talk a bit about how we do that. To do that, we introduce an auxiliary graph, which we call the blueprint, and that is designed to help us find these special monochromatic type components. Okay, so we start out, with H, our red, blue, edge colored almost complete foregraph. And from that, we construct a graph G, the blueprint. Okay, so this will also be red, blue, edge colored. And almost complete. But it will be a graph, just a normal graph or a two graph. Okay, so it will be easier to handle. Okay, so how do we construct this blueprint that will help us find these matchings? Okay, so for simplicity, we'll assume that H is complete. So it's actually almost complete, but that doesn't make too much of a difference. So if H is complete, G will end up being complete. But if H is almost complete, G will end up being almost complete only. Okay, so how do we construct this blueprint? So we'll construct it here. So the blueprint G. Okay, and it lives on the same vertex set as H. So V of G is the same as the vertex set of H. Okay, so if H is complete, it will turn out to be complete. So basically, we only have to decide how do we color each edge, either red or blue. Okay, so consider any edge. We'll pair vertices X and Y. Then to determine how we will color them, we look at what is called the link graph of H with respect to X and Y. Okay, so what is the link graph? So the link graph has an edge UV if and only if XY UV is in H. Okay, and of course, if H is complete, this is pretty meaningless because it just means that the link graph is also complete, but we also inherit the coloring. So for example, if we have UV here and the 4H XY UV turns out to be red in H, then we color this edge here in the link graph red as well. Okay, and then this way we color all the edges here in the link graph. And so on. Okay, and then now if you remember back to the very beginning of my talk, we did this little exercise that said if you have a red, blue edge colored complete graph, then there's either a red spanning tree or a blue spanning tree. Okay, so in particular in this link graph, there will be the red spanning tree or a blue spanning tree. Okay, so let's say there's a red spanning tree and we'll call it KXY, red spanning tree. Okay, so And then if there's a red spanning tree, that's how we decide to color the edge XY in the blueprint red. And if it was a blue spanning tree, we would color the edge XY blue. Okay, and of course we do this for all the different pairs XY or vertices of H. So get some coloring of the complete graph here as our blueprint. Okay, so now why is this blueprint useful? So the first property we're going to look at is we have that the set of edges UVXY, where UV is in this red spanning tree KXY, is contained in a red tight component. And let's call it RXY. Okay, so why is that? So remember KXY is connected, so if you have UV and UW in KXY, then this simply means that UV XY and UW XY are red edges in H. So they're in H by the definition of the link graph, and they're red because KXY was a red spanning tree. Okay, and of course these two edges share three vertices. So they are tightly connected, and then because KXY is connected and two connected edges here end up sharing three vertices, this tells us that all the edges have to be in the same red tight component. Okay, so basically this means that every edge in the blueprint induces a tight component of the same color in H. Okay, and now second important claim is that if we have XY and XZ, two red edges in the blueprint, then it actually turns out that they induce the same red tight component in H. So RXY is the same as RXZ. So why is that? So what is the situation we have? We have X, Y, and Z, and XY is red and XZ is red. So if XY is red in the blueprint, what does this mean? Then, so if you go back to our picture of the link graph HXY here, somewhere, because this is a red, KXY is a red spanning tree here, somewhere here will have to be Z, okay? And then there will have to be some other vertex Z prime, such that Z prime is a red edge in this red spanning tree, okay? And so this means that there exists some Z prime such that X, Y, Z, Z prime is a red edge in H and is also, of course, by definition in the red component induced by XY. And then we do something similar. Similarly, there exists an vertex Y prime such that X, Y, Z, Y prime is a red edge in H and also in the tight component induced by XZ. And now because X, Y, Z, Z prime and X, Y, Z, Y prime share at least three vertices, they are tightly connected, and so because one of the edges came from Rxy and one of them came from Rxz, this means that those are actually the same red tide components. So we get what we wanted. Okay, so what does this now mean? So we get our key fact is that red components in the blueprint correspond to red tide components in H in the original graph. Right, because we showed here if two red edges are touching, then they induce the same red tide component in H. Okay, so that meaning that any red component in G, all the edges in it will induce the same red tide component in H. Okay, and now if we look at G, it is a red-blue edge-colored complete graph. So again, by the exercise, we'll contain either a red spanning tree or a blue spanning tree. So say it contains a red spanning tree. So now G contains a red spanning tree. So this will mean that actually all the red edges in G induce the same red tide component in H. Okay, so basically there's this one special monochromatic tide component in H that we can always find in this way. And so both our proofs start by choosing a maximum matching in this tide component. Okay, and then that might not be from the beginning the right choice. You might have to then later switch to a different matching or find a second matching, a blue matching maybe, and so on and continue. But this is how we start in both our proofs. Okay, so that's everything I will say about the proof, and then I'll finish up by mentioning some open question. So first open question, can every red-blue edge-colored K4 be partitioned into two monochromatic tide cycles? Now, this would be an analog of a result we have for the free uniform case and would be an exact result. And again, here you have to say two monochromatic tide cycles instead of a red and a blue one, because there's a counterexample showing that if you insist on one red and one blue one, you cannot do it. Okay, so second open problem, can every red-blue edge-colored K and K be approximately partitioned into red and the blue tide cycle? So this was already known for the 3 uniform case. We showed it in the 4 uniform case. And in the 5 uniform case, we were only able to do it with 4 monochromatic cycles, but we really believe this should be true. And so maybe it is also true for general uniformity as well. And then, of course, Pokrovsky's conjecture is still open for all R, at least 4. Okay, so that's all I have. Thank you very much for your attention.